Good afternoon, or let's say better, good evening. I know it's quite late and most of you are looking forward to a nice dinner and some drinks, me too. But I hope I can catch your attention for the next 15 minutes. Do I have the, here it is. We are one of the leading suppliers of satellite monitoring and geolocation solutions, and our systems are ground-based systems. They are pure passive, so we are not transmitting anything to the satellite. We are just receiving the RF spectrum and try to get out as much as possible from the spectrum. And that's why it's also called mastering the intelligence spectrum. We are not new on the market. Our system dates back to the late 90s. So we have more than 20 years of experience in this area, in this domain. And our system is called SkyMon, and it provides, in the meantime, all the necessary tools for satellite operators to monitor their satellites. In this presentation, I will focus on two use cases. One is the third from the left. It's about geolocation of VSAT terminals, and one is about monitoring of LEOSAR, the last one here in the list, to protect critical infrastructure. We all know the sky is quite crowded, so there are more than 10,000 active satellites orbiting the Earth. Most of them are LEO and MEO satellites, and to get visibility on what's going on in sky is critical and necessary to enhance national security. And one part of this visibility is to understand the electromagnetic spectrum. And this can be done from a strategic point of view in order to predict the future or upcoming threats, to anticipate decision makings, or as a tactical system, from a tactical point of view, to identify and geolocate and monitor the enemy. We distinguish here between COMINT and ELINT. So the first use case is related to communication intelligence, basically to detect and identify and geolocate communication. And the second use case I will focus on is ELINT, electronic intelligence. It's intercepting and processing of radar signals to protect critical infrastructure, with the goal to get as much information out as possible from the spectrum in order to create appropriate countermeasures, for example, jamming the radar signal to avoid scanning of critical infrastructure. Let's start with the first use case. It's about VSAT monitoring and geolocation of VSAT networks. The main characteristic of a VSAT network is that several users are sharing the same frequency. In order to do that, they are applying TDMA technology, meaning that each user gets his own time slot, his own frequencies, in order to avoid interference with the other users in the system. And this is all managed by a gateway. So the gateway is creating a time burst plan, which is broadcast to all of the users, the VSAT terminals. And in this time burst plan, you have a concrete plan for each of the terminal on which frequency and which time slot they can transmit their data. You can see this here in the middle in this picture. You see on the horizontal axis the frequency. We have here 5 different frequencies, and on the vertical scale you have the time scale, and the different color of the plots are showing the different users. And you see even in the time scale as well as in the frequency scale, there was the jump from one time slot to the other and from one frequency to the other. Now, in order to be able to monitor and even specifically geolocate certain VSAT terminals, you have to extract the data bursts transmitted from a specific terminal. And this can only be done if you know the time burst plan. The problem is the time burst, although there exists a standard for the time burst plan, it's a DVB-RCS standard, most of them VSAT manufacturers are using their own proprietary technology and proprietary protocols. And this time-burst plan is not released, is not public known. So it's protected information. And we spend a lot of effort and time in order to, via reverse engineering, to find out for some of the VSAT technologies how this time-burst plan is structured. And with this knowledge, we can have access to the individual bursts. This is what we call burst extraction. You can see here an example. The result of such a burst extraction is you get a list of all the active terminals with the unique terminal ID, with all the parameters, carrier to noise, the number of bursts which have been identified, and so on. You can even see a spectrum, a power versus time spectrum, and we can really identify each individual burst for specific terminals. And with this knowledge, we can apply then our geolocation methods. The time in this presentation is too short to explain in detail how this geolocation is working, but it's basically using two methods. One is called time difference of arrival, and one is called frequency difference of arrival. You see here on the map two lines. They are representing the result of these two methods. And then at the intersection point of these two lines, this is the calculated position of the VSAT terminal. This is the most accurate method to geolocate the VSAT terminal. The accuracy is in the range of 1 to 3 kilometers in average. It depends on some parameters. But we can reach, with this method, we can reach the same accuracy as we are doing geolocation of standard SCPC signals. But as I said, the limitation is that we only know for some of the VSAT technologies the time-burst plan, and it would be a too big effort to find out the time-burst plan for all the VSAT technologies from all the VSAT manufacturers which are on the market. So that's why we have investigated in methods which are working completely independent from the underlying VSAT technology, meaning that we try to find out similarities in the bursts, because you can assume that data bursts which are transmitted from a specific terminal will show the same characteristic. They will have more or less the same power level, they have the same core stock to the core pole, they are using the same modulation type and things like that. So there are quite a few similarities, and by applying statistical methods on the data stream, you can potentially identify bursts which are coming from one specific terminal. And we are grouping these bursts, so we are extracting these bursts again from the data stream. We are grouping these bursts, and then we apply our geolocation methods on these grouped bursts, and then you can see the result is the same on the map. It's not that accurate because the statistical method there were always bursts in which are coming from other VSAT terminals, so it's not 100% accurate. And the other disadvantage is you do not get the unique terminal identifier, because with this method we are not able to really decode each and every single burst. But we can even geolocate the position of the terminal. And by combining both methods, what we are doing in the system, we can potentially geolocate each and every VSAT terminal completely independent of the used VSAT technology. Coming to the second use case, this is about LEOSAR monitoring. And a SAR satellite, a synthetic aperture radar satellite, is a satellite which transmits a radar signal to the Earth to scan the surface of the Earth with the goal to create images of the Earth. This technology is invented to emulate, let's say, a super large antenna. The bigger the antenna, the emulated antenna, the better is the resolution. The problem is maybe you want to protect your critical infrastructure of being scanned from such a LEOSAR satellite. And this is exactly the goal of our LEOSAR monitoring system. We try to detect on your critical infrastructure when a SAR satellite is starting to scan this critical area. then we try to catch the radar signal. We try to characterize the radar signal. And we try also to find out which satellite it is. So we try to track the satellite. We try to calculate the ephemeris data, so the position of the satellite. With this information, with the radar signature and the ephemeris data, we go into a database. There was some public databases available, or the customer has its own SSA database to see if this satellite is already known in the database. Then we know exactly which satellite it is, or it is a new satellite which is not part of the database, or a potential spying satellite which is not for sure part of any catalog. We did this. It's not finished. The product is not yet available, but we did a proof of concept in our lab in Aix-en-Provence. It's in southern France, close to Marseille. The target satellite was a Copernicus Sentinel-1A. And we used this antenna, which you can see here in the middle. It's a wideband antenna operating in the frequency range from 0.5 to 6 gigahertz. And it has a wide angle of roughly 30 to 40 degrees. And you can see here the Copernicus satellite. It's moving from south to north. And you see on the right side, this is the scanned area. And where the green bubble is, this is Aix-en-Provence, where we have our system located. And we could retrieve the signal for about 20 seconds. And in these 20 seconds, we could classify the signal. We could identify the signal. You can see here an example of the spectrum which we have, of the radar spectrum which we have recorded and analyzed. We can even make visible the individual pulses. We could measure the pulse duration. So we could really characterize the whole radar signal. So and the next step is then to track the satellite, to calculate the ephemeris data, which is a quite challenging task because for tracking the satellite, usually you need to receive the signal for a quite longer time instead of a couple of seconds. But this is then the next step. Okay, this LEOSAR monitoring system is again a ground-based system, and it can be used to protect your critical infrastructure, to know exactly when your critical areas are scanned or possibly scanned, and then you can take the appropriate countermeasures, creating maybe an anti-jamming signal to avoid of being scanned in this area. I'm at the end of my presentation. Thank you very much for your attention. And if you have further questions, I'm available afterwards.